Things are getting desperate. It's 9 o'clock and one person is here, now two. I know the track guys are supposed to be gone today, but we still should have Jake Woosley and Riley and Yi Chen. Morning. I was just lamenting that so few people were here.
I'm here.
Yeah, I see you, Elvis. So Elvis, for today, there are going to be two worksheets. One is posted under yesterday's date and one under today's date. We just didn't get to the one from yesterday, so you might want to look those up. I'm going to pass a few things out right now. This is the first worksheet we're going to be doing after a little discussion. Okay, well, I'm assuming that hopefully Yi Chen will be on his way and Jake Woosley will be here shortly, but let's just get started. Let's see, something's gone blurry here. Yeah. We're going to now, so far we've been sort of thinking of things in terms of a description of the electron in the hydrogen atom. And we've been describing the spin of the electron, but our Hamiltonian, in other words, the energy, potential energy, doesn't have anything to do with the spin of the electron. But that isn't necessarily the case. We can imagine physical situations where the spin, the energy does depend on the spin. And as we talked about last time, you may have some memory, and we're going to try to develop or at least remind you of your intuition about magnetic moments in magnetic fields and why they tend to want to align with applied magnetic fields, which means when you have charge spinning, you have a magnetic moment. And when the magnetic moment is anti-aligned with the field, pointing more or less opposite, it's in a high energy state. It wants to flip around and align with the field. So that's a lower energy state. That means there's a potential energy associated with that rotation angle, right? You're going to a lower potential energy when you align with the field, higher potential energy when you anti-align with the field. So if we're thinking of an electron, of course, there are only two kinds of states if the applied field is along the z direction. So here I'm going to follow Griffith's notation and say the magnetic field has strength B0 and it's along the z hat direction, which for whatever reason I was writing as k hat here, same as z hat. And we want to kind of remind ourselves of the idea of the magnetic dipole moment. Anytime you have, sort of a very crude model of a magnetic dipole moment, or a simple one would be a loop of current. This keeps going. So if I have, some sort of loop with current I, and at least if it's a planar loop, and there's an area A for the cross-sectional area of that loop that would span the current loop there, then the magnetic moment of this current distribution is given by, its magnitude is I times A, and the direction of it is given by one of many right-hand rules from electricity and magnetism, where you take your right hand curl it along the direction of the current, and then your thumb points in the direction of what we're going to call the magnetic moment, mu. So magnetic dipole moment points along that direction. It's supposed to be, you know, sort of normal to that surface. And the magnitude of mu is just the current times the area of the loop. So we're going to kind of develop that a little bit in a worksheet. Oh boy, this camera just can't stay focused. We're going to develop that in a worksheet. And I think that's all I have to say about it. So let me orient you to the worksheet. This is one I passed out to a couple of people in class. Alvis, this is the one that was posted under yesterday's date. And it's got a little square current loop on it. Let me try to draw the picture associated with this on the board at a large scale. So we've got, instead of a circular current loop, which was what I was kind of suggesting there, we've got a square current loop, and I've drawn it in X, Y, Z axes. So I'm going to draw it kind of large here. I tend to like X to come out of the board, Y over there, and Z straight up. And the idea is our square current loop doesn't lie in the XY plane, but it's actually tilted around the X axis. And so I drew a little dashed line here that, or a dashed curve that doesn't correspond to our current loop. It's going to help us visualize our current loop. So there's where, if our current loop were lying in the XY plane, it would be where the dashed curve is. But now we're going to rotate it around the X axis, which goes right through the center of this square piece. So it's up by an angle theta. And I did a pretty good job of drawing it on here. Let's see if I can repeat that. Oh, it should be going through this right there. It's supposed to be as if it's pivoted along this line through the center up by an angle theta out of the XY plane. And we've got a current I, so this is supposed to be a conductor forming a square loop. We've got a current I in it, and we're told in here that the lengths of each of these four sides are L. Okay, and what we want to do is, work out what the potential energy of this current loop is as a function of theta. That's what we're trying to figure out here. This is, you probably didn't go into it this deep in physics 230. We might talk about it at this level in physics 350, although it's certainly kind of a physics 230 kind of analysis we'll do here. So the first thing we're going to do is we've labeled, there are four sides to this current loop. I've labeled them side or leg A, leg B going along the back there, leg C, and then leg D going along the front there. We want to figure out what the force vectors are on these four legs. And we got to remember the force rule. Oh, and I should draw the magnetic field here. Magnetic field points along the Z direction. So we'll say it's strength B0 and it's in the Z hat direction. So I've got current going in a magnetic field. So let's just think about leg A here, this one that's tipped up in that direction. It's flowing in the minus X direction along leg A. Everybody with me there? So, when you first talk about magnetic forces, you talk about QV cross B, but then you re-express that in terms of a current element, right? And you would say something like this in your physics 230 class. If I have a little bit of current, or a little bit of, well, let's just say, if I've got a little bit of a differential amount of path length along there, so I step along the direction DL going from there to there, there's a little bit of force on that bit of current there. And a little bit of force is I times dl cross b, where dl points in the direction of dl and it's differential. And of course, that little bit of force, since I isn't changing direction for the whole leg here, if I want to calculate the force for the entire leg, I might write that as F on a particular leg is going to be equal to I times the total length cross B of that leg right there, right? All I've done is integrate this from here to there and find the total force on this, right? So I've divided it up into a bunch of little DLs. They're all giving the same contribution because the DLs are all pointing along the same direction. Now, the direction of all these DL cross Bs is what? Let's just think about it for leg A here. If I take DL, which is pointing, this is kind of a perspective drawing, but I'm thinking of the x-axis is coming out of the board. Here, the current is going into the board, right? So it's DL cross B, which is up. My right-hand rule for cross products, fingers along the first one, curl towards the second one. DL cross B is going to point in the plus y hat direction, right? So that means for this particular leg of the loop, the total force on that leg is going to be pointing, I might call that F on leg A, is pointing in the plus y direction, directly to the right in our diagram. Okay? And we can figure out what the magnitude of that force is. This should be a force vector there. If I want to figure out what the magnitude of the force is, well, on this one, of course, the L is exactly perpendicular to B. So the magnitude of this cross product is just the magnitude of L times the magnitude of B. If two vectors are perpendicular and you take their cross product, then the magnitude of the cross product is just the product of the two vectors, right? If they aren't perpendicular, you have to have that sine of theta factor in between them. But if they're perpendicular, and in this case, they are perpendicular, because this is going straight in the minus x hat direction, the current straight into the board. So I could write the force on leg A is equal to, well, let's see, we already figured out it's in the minus I hat direction. So that takes care of the direction vector. And now we just need the magnitude of it. And the magnitude of it is I L times the strength, if we're saying each one of these legs is of length L, times the strength of B, which is B0. And it's pointing to the right. Sorry, and I'm not sure why I put a minus I hat here. We decided it was pointing in the plus y direction. So that should be a plus y hat. If I'm saying something that doesn't make sense, call me out on it. Okay, so that's the force on this one. Now what I want you to do is think about writing it out the same way with the direction vector and the strength of it, what the force is on B and C and D. And then we're going to use those to figure out what the net force is on this current loop and what the net torque is on this current loop. Those are parts B and C. So A, you're supposed to find the individual forces giving components on sides A, B, C, and D, and then add them all together in B, and then think about it in terms of torque in C. Then we'll stop and maybe do the rest together. Okay, let's maybe do B together just to make sure that we're not too far off on things. B is a little bit more complicated than this one because, so what I'm drawing is leg B here, but I'm visualizing it just in it, it lies in the YZ plane. So why not just do the YZ projection like that? And we won't have to think three-dimensionally for this one. So here's leg B. Again, all of these legs are of length L. So that's length L. And that means this part is length L over 2. And I've got to calculate the same cross product here. So I have I. Unfortunately, that L vector and the B vector aren't perpendicular anymore. So I'm going to have to think about how to calculate the magnitude of the cross product. So certainly, one way to do it is just to say, let's take the component of L, which is perpendicular to B, times the magnitude of B, which is B0. And we've got to figure out that, right? We would say, when you're doing a cross product, the component of a vector that you're crossing with another one that's parallel to that vector just gives a 0. So it's only the perpendicular component that gives a non-zero contribution. So if I just pick out the perpendicular component of this vector L, and the perpendicular component is going to be given by this distance right here. Well, that's half of it anyways. I guess the perpendicular component would be given by this whole distance right here. What I'm darkening in there or lightening in with the chalk is what I would call L perpendicular. This is the vector L, the component of it perpendicular to B is going to help me do the magnitude of the cross product, right? Because I would say, the component parallel to B gives nothing. So we only want the perpendicular component of L. If this is of length L, this is L over 2. This is L over 2 cosine theta right here, right? And we need to double that, right? We have 2 L over 2s cosine theta. So I could write that as maybe I'm making this too complicated. 2 times L over 2 cosine theta times B0. And of course, the 2 and the 1/2 cancel out. So it looks, and okay, so that's the magnitude. And I need to put in the direction. What should be my unit vector for DL cross B in this direction in terms of x hat, y hat, and z hat? Negative x hat, right? I do fingers along the first vector in the cross product, curl towards the second one. That gives my finger going into the board, which is the minus x hat direction. So I should, this is a vector, so I better put on the direction by hand. And so, just to simplify, this is IL B0 cosine theta with a minus sign and an x hat there. Okay, so that means in my diagram, the force on this leg is going in that direction. Force on this leg is going back into the page minus x hat direction. So here I would say FB goes in that direction. FC, not surprisingly, has the same magnitude as FA, but it's going in the opposite direction because I've just switched the direction of the current on that side. So FC will be in this direction, the force on leg C, directly in the minus I hat direction. So running out of room here. Let's see if I can squeeze it in over here. FC should be the same as FA, IL B0, but it's in the minus y hat direction. And FD is going to have the same magnitude as FB, except again, only thing that's changed is the current direction. So it's going to be coming out of the page. That's my FD direction. So those are the directions of the forces on the 4 sides of this square current loop. Same magnitude, but all that's going to change is the sign. So it will be a plus IL B0 cosine theta x hat. Okay, everybody okay with those forces? I just don't know how much that I dl cross b is burned into your brain from physics 230. That's something you definitely did back there. Okay, so if I do this, first of all, what would you say the net force on this entire square current loop is?
0.
It's going to be 0 because this has the same magnitude as this, and this has the same magnitude of this, and they're in opposite directions. So the net force is 0. That's B. Now the net torque I can see is not going to be 0 because, well, this force and this force are just trying to stretch out the current loop, and they're not trying to rotate it in any direction. You know, you could think of your axis for the torque as being about the center. These two forces are going to try to straighten it out and rotate it in that direction, right? So they're going to exert a torque on the current loop, which is going to try to twist it around the x-axis in, you know, in the direction minus x hat in the usual sense of torques, right? Whichever, if you curl your fingers in the direction that it's trying to twist it, your thumb points in the conventional direction that we assign to torque. And so that means, well, let's see. Again, to figure out the torque, let me erase this stuff. I'm going to need my FA and my FC to calculate the torque. FB and FD don't contribute any torque because they're kind of moment arms about the axis or 0. But let's calculate the torque. And again, let me draw a projection. Well, probably it's best to just use this diagram here. I'm saying there's a leg over here which has FA on it, right? And there's a leg coming out of the board here which has FC on it, and they're trying to rotate it in that direction. That's a torque direction of minus x hat. And to calculate the magnitude of the torque, what we can say is, well, let's calculate the torque due to each one of these. We'll add them together. And we can just do the magnitude of the force times the moment arm for that force. And to get the moment arm, you always say, draw the line that contains the force vector and look for that perpendicular distance to the axis about which it's going to start rotating. So this is the moment arm right here. So if this is L, let's see, let's just calculate the torque due to this one, and then we'll just double it to get the other. Okay, so that's L. This half of it is of length L over 2, right? That's L over 2. The moment arm is going to be L over 2 times the sine of theta would give me that side or that side. So to calculate the torque, just due to this one side, I would say it's the force on A, magnitude of that force, ILB0, that's how big the force was, times the corresponding moment arm, which is going to be L over 2 times the sine of theta to get that moment arm. Okay, and that's the torque due to just one of these forces. Of course, this one is exerting an equal torque there, so I just need to double it to get the total torque. And if we want to make it into a vector, we kind of know it's trying to twist it in what we call the minus x hat direction. Okay, so just to simplify, the 2 and the 1/2 cancel. That's equal to IL squared B0 sine theta in the minus x hat direction. Okay. That's our torque expression. Now what we want to do is associate a potential energy with this, right? We can now that we know the torque, we can see, well, where is the torque going to be 0? For what angles is it going to be 0? Well, it's going to be 0 when the sine of theta is 0, and that's 0 when theta equals 0. That means it's aligned like this, completely flat. or at theta equals pi when it's anti-aligned in that direction. And the torque is always going to be trying to twist it back to the theta equals 0 direction, right? We said when it's at another angle, it's trying to twist it back towards being in the theta equals 0 orientation. Okay, so the potential energy is actually minimum at theta equals 0. It's maximum at theta equals pi. There's also no torque at theta equals pi, but it's an unstable equilibrium. It wants to flip back over. And at any other angle, it tries to get twisted back to 0. Let's try to get an expression for the potential energy associated with this. Yeah, Jake. Well, I'm just imagining that we're holding it in this direction and we're trying to figure out the torque due to the current being in the magnetic field at this direction, right? But you know, I didn't really tell you what theta is, so you could imagine theta being 0 or theta being pi where it's flipped over or something in between. I just kind of drew an arbitrary one there, but we're not imagining it moving necessarily, but just in any configuration, what would the torque be? And it changes. The torque is 0 when it's completely flat. The torque is 0 when I completely flip it over, but that's an unstable position because as soon as you give it a little tip, it's going to flip back over and want to be in that configuration. So the torque is maximum when theta equals 90 degrees, when it's pointing up like that. Okay, so potential energy is a minimum when theta equals 0, and now I want to find a potential energy function. And I'm not sure, again, how you know, if you took advanced mechanics, you certainly talked about things like this. Just like I could say the relationship to a force X component to the potential energy is given by, you know, the force is a negative gradient of the potential energy. Similarly, if you have some torque that is, you know, a function of angle, the relationship of the torque to the potential energy is the torque is equal to minus the rate of change with respect to that angle of a potential energy function, which I don't know if people use U for potential energy. We've been using V in this class, but you know, in classical mechanics, sometimes people use U. I'm not sure, what do you use in Locket's class? Does he use a U? Yes? Yeah, okay. T and U. Sometimes people use V in classical mechanics too. In any case, that's our potential energy. So I want to find a potential energy function, which is a function of theta, right? You're going to have high energy states where it's flipped over, low energy states. What's the energy as a function of theta? And we're going to say the definition of the potential energy is when we take the negative rate of change with respect to theta, that's going to give us the torque. Okay. So I need to find a function so that when I take the derivative of it, I get it with respect to theta, I get sine of theta. Of course, I want a cosine in there to give us that. So let's just try to construct what the potential energy has to be as a function of theta. I need all these things out in front, I L squared B 0. I want a cosine of theta in there. And it's unclear to me whether I need a minus sign out in front, but let's just check it, right? If I take the derivative with respect to theta, I would get, derivative of cosine is minus sine, I would get exactly this function. But we don't want to take the derivative with respect to theta and get the function we derived. We want to take negative the derivative with respect to theta and end up with this function, which means my potential energy also needs an extra minus sign out in front, because when I take the negative derivative with respect to theta, that negative cancels out this one, and when I take the derivative of cosine, I get minus sine, which is exactly what we had up there for the torque magnitude. Okay, so this is what our potential energy is as a function of theta. And again, just for a sanity check, we're saying this is going to be at its lowest position because of that minus sign when theta equals 0, right? When theta equals 0, cosine is 1, and this is the most negative it's going to be. When theta equals pi, cosine will be -1, which then cancels this minus sign and gives us the highest potential energy it's going to be. So it's going to want to flip over kind of when it's near theta equals pi. Okay. Now, let's go back. That I know this is a long digression, but it's just to make sense of the Hamiltonian we're going to write down. Let's re-envision this in terms of the magnetic moment of a current loop. We said if you've got a current loop with current I in it and it has cross-sectional area A, at least if it's a planar current loop, and this one is planar, then the magnetic moment will point in the direction according to the right-hand rule, and the magnitude of the magnetic moment is going to be I times the area of the loop. Here, the area of our loop is L squared if the length of each leg is L, right? So this is our A, here's our I. We could also write this as minus the magnitude of mu times B0 times the cosine of theta. And notice that when we have, this is the size of the magnetic field, this is the size of the magnetic moment. We've got the magnitude of one vector times the magnitude of the other times the cosine of the angle between them. That's the same thing as the dot product between those two. So I could finally write this as minus the mu vector dot B. The point of the worksheet is where you see this just appear in Griffiths, and maybe it doesn't make any sense if you haven't thought through it, but I'm trying to lead you through the details of why this expression is telling us about those torques. Whenever you have a current loop, right, it's going to feel a torque if it's not aligned in the right way with the magnetic field. Any questions on that derivation? It's not one of the central parts of what we're learning in this course, but you'll see Griffiths, I think, just plunks this down and assumes you kind of know where it came from, and a lot of times people haven't thought about it. Okay, so did a lot of work. Ending up with the potential energy is minus mu dot B, which means, think about this, when mu is aligned with B, the potential energy is most negative. That means it's the lowest value. That means it's stable when mu aligns with B. When mu is anti-aligned with B, that means the dot product will be negative and the whole thing will be positive. That's the highest potential energy. Okay, so here's where Griffiths comes in and says, you know, we haven't put anything into our Hamiltonian that had to do with the spin state, and we're going to put something in that has to do with spin because the magnetic moment is related to spin in a particular way, right? Spin tells us about something about things moving through space. Spin angular momentum tells us about how mass is circulating around, right? That's spinning. But when mass circulates, if it's a charged particle, charge tends to circulate at the same time. And so we've made kind of a current loop. And so it's going to generate a magnetic moment. So Griffiths suggests, again, let's forget about the spatial part of the Hamiltonian. If we're talking about a hydrogen atom, of course, this wouldn't be the only part of the Hamiltonian, but this would be some extra potential energy just associated with the spin if we put the electron or the whole hydrogen atom in a magnetic field. Right? There's going to be some potential energy associated with how its magnetic moment vector is lined up. Okay, so again, if we've got a, you know, something like a proton, the proton is spinning in a circle, then when it's spinning in that way, angular momentum would be to the left in the picture if it's spinning from the bottom out of the page towards in at the top. Okay, and lost control here. That means that since this is positive, it seems like if the mass is spinning in the direction to give the spin angular momentum to the left, that since it's a positive particle, the positive charge would probably also be circulating in that direction. And so it's kind of like a current loop wrapping out and around like that. And that would give a magnetic moment vector along the same direction as S. So if we know something about S, we know something about the magnetic moment vector. Now we've got an electron. An electron's a negatively charged particle. So if it's spinning in the same direction that I assumed for the proton, so that its spin angular momentum is to the left in the image, I've got what seems like some negative charge spinning in a circle like this, right? And negative charge spinning in a circle like this is equivalent to a conventional current spinning the opposite direction like that. That would give me a magnetic moment in that direction to the right. And so for negatively charged particles, the magnetic moment tends to be opposite the direction of spin angular momentum. This is just a picture. Of course, we're told we can't really think of spin as a spinning charged ball or something like that, but it seems to make sense that these two would be anti-aligned. Okay, so and we do find that, you know, for each charged particle that has some mass and therefore has some spin. Spin might be zero, but whatever the spin is, it seems like the magnetic moment would be proportional to the spin. It might be negatively proportional in the case of a negatively charged particle, or positively proportional. There's no guarantee the charge is distributed the same way as the mass, so it's no way, you know, we would have to experimentally determine what this constant of proportionality is. So people just define something and say, well, mu is some constant times S. And, you know, if we're talking about an electron here, we would call this this gamma constant of proportionality, the electron gyromagnetic ratio. And that number is negative for negative charged particles. It's positive for positive charged particles. So we need to remember in what goes on here, we're going to express things in terms of gamma. But if we're thinking about an electron, gamma is a negative number that might help us make sense of which way forces and torques are going to be applied. Okay, what's the importance of this? Well, we already have spent some time thinking about spin angular momentum. So now we'll be able to turn that into some knowledge about the magnetic moment, which feeds into our Hamiltonian. Okay, so if we substitute that in just for our mu here, mu is equal to gamma S. So our spin Hamiltonian part is going to be minus gamma B dot S. Okay. Again, to simplify things, let's assume that B is along the z hat direction with magnitude B0. And therefore, when we take this inner product there, we just pull out the z component of the S vector, right? We take the inner product of S with something only along the z direction, pulls out the z component of that spin angular momentum operator. Okay, so that's still an operator, right? We did the dot product with the vector parts, but this SZ is still an operator, right? The Hamiltonian's an operator. This is sort of the non-trivial part of the operator right there, SZ. And we worked really hard earlier on to figure out what the matrix elements of SZ are. So I've substituted them in here. We found it was h bar over 2 times 1, 0, 0, minus 1 as a 2 by 2 matrix in that usual spinor basis that we've been dealing with for the last couple of days. So it looks like the spin Hamiltonian is proportional to SZ, and therefore the eigenvectors of the spin Hamiltonian will also be the eigenvectors of SZ. And we can see what the eigenvalues are going to be, right? So I guess I'm writing it here. If we call the eigenvectors or eigenstates of SZ chi plus or minus, right? Chi plus is spin up along the z direction, chi minus is spin down along the z direction. These will also be eigenvectors for our spin Hamiltonian, but the eigenvalues corresponding to spin up and spin down, that's what the plus or minus subscript means there, will be these numbers that appear out in front, minus or plus, right? So if the particle is spin up, it will have a negative energy, And if the particle is spin down, it's going to have a positive energy eigenvalue. And it's just that stuff out in front, just like it was an h bar over 2 or a minus h bar over 2 for SZ. Same kind of thing. And again, we got to remember to make sense of this that gamma itself for an electron is negative, and therefore, when we have the spin up state for an electron, that's going to come with a plus sign for the eigenvalue because gamma is negative, and that means it will be the higher energy state. And when it's spin down, that means it's anti-aligned spin with the magnetic field. It's going to be the lower energy state. That's going to be the unstable one that's going to want to kind of flip over. It's going to feel a torque in that direction. Okay. Now, let's put in the time dependence here and think about the time dependence. Suppose in this usual spinor basis, we say at time t equals 0, let's write down the spinor as some arbitrary, say, normalized state. So a squared plus b squared equals 1. It's in some random spin state, the electron, at time t equals 0. How do we get that spin state as a function of time? Well, we do the same thing we always did. What we do is write it as a linear combination of states of definite energy at time t equals 0. So we write it as a times chi plus, right? That's just 1, 0. Plus b times chi minus, that's 0, 1 at time t equals 0. And then to put in the time dependence, in each of those terms, we put in the corresponding exponential factor that puts in the time dependence, right? So corresponding to the plus 1 here, we need e plus up there. Corresponding to the spin down one there, we need the e minus that we defined up there. And that gives us the time dependence. Writing that as a 2-element column vector, this is what it looks like. Okay. It's hard to kind of visualize what that means or get any sensible, information out of it. Sure, the upstairs and downstairs are going to change as time goes on. They've got these weird exponential complex factors going on them. But Griffiths suggests a way that we can get more insight into this by thinking of, for this state, what is the expectation value of Sx and the expectation value of Sy and the expectation value of Sz as a function of time. So write each of those as a function of time. Expectation values of operators correspond to the closest thing that we have to a classical kind of picture of what's going on. We have this, it's not going to be classical, but if something had almost a definite angular momentum, then the expectation value of Sx would correspond very closely to the Sx that is close to in the classical case. So let's compute what the expectation values of the 3 components of spin angular momentum operators are as functions of time. And we know how to calculate expectation values. So just for example, let's look at Sx. To calculate the expectation value of Sx, what we do is put it in our arbitrary state as a function of time, right? This is our a, b with the exponentials in there. We sandwich Sx between it, and Sx is a matrix operator. So in terms of what we talked about for how to take inner products, right? When something's on the left side of the inner product, we write it as a row vector. And then we've got this as our matrix here, and this is a column vector. Now, somehow I skipped over an important piece here. Griffith says, let's just, to simplify things, we know that the sum of the squares of these, this is going to be in a normalized state. We better have the sum of the squares of these add to 1, right? If 1 is 1 over root 2, the other one better be 1 over root 2. Or 1 is 1, the other one's got to be 0, and so on. This seems like a weird way to do that, but cosine squared plus sine squared of anything always adds up to 1. So let's just, instead of writing down a, let's substitute for a, cosine alpha over 2. And b is sine of alpha over 2. Then certainly a squared plus b squared is cosine squared plus sine squared of something, which is 1. Okay, we've reduced it to 1 parameter now. It's unclear why the alpha over 2 is in there, but we'll see that in just a second. So We've substituted for A and B there in these expressions with cosine alpha over 2 and sine of alpha over 2. And we're going to calculate this expectation value, which is an inner product. We talked about how to take inner products for column vectors. You know, the stuff on the left turns into a row vector and you have to put in the complex conjugate, right? I didn't put in the exponentials there, but that would have a plus I on those on this side. These would have minus I's on those. So I've left out some of the details there to not make it too big of a mess. When you do that, right, I do the matrix multiplication here, and then I take the inner product with this stuff. Here's what comes out of it. So the expectation value of Sx, don't worry about it too much right now. We'll interpret it in a minute. It ends up being h bar over 2 times sine of alpha times the cosine of gamma b0 times t. Okay, the cosine's coming from some combination of those complex exponentials. You could do the same thing for Sy and Sz. Sy ends up being this and Sz ends up being this. And at this point, thinking about these three together, we can start to interpret what that alpha is geometrically. Up to now, it was just a definition. But if we draw some three-dimensional axes, so let me display the board. You know, I'm going to write some stuff on the board. And before I do that, let me just say, let's just call this thing in parentheses here phi. Okay, so the thing in parentheses, gamma b0 times t, I'm going to call phi. And let me write on the board before I take this off the screen that we just found that the expectation value of x spin angular momentum is h bar over 2 sine alpha cosine phi for my definition of phi. Sy expectation value is h bar over 2 sine alpha sine phi with a minus sign in front of it, right? And the expectation value of Sz is h bar over 2 cosine alpha. All right. Now let's go to a three-dimensional coordinate system and try to visualize this. See how well I do with this. Here's x coming out of the board. Here's y. Here's z. Let's imagine I've got some, vector pointing out in three-dimensional space. And to make it look three-dimensional, I'm going to sort of project it down into the xy plane. So here's kind of where the shadow of that would lie in the xy plane. Let me also draw the shadow of the entire vector down here like that. Notice if this vector had length h bar over 2, then if I project it onto the z-axis, I'm not sure if this is clear what I'm doing that. I'm sort of projecting onto the z-axis. If we interpret this angle as alpha, and this is h bar over 2, wouldn't the projection onto the z-axis be h bar over 2 times the cosine of alpha, which is exactly what we have there. Right, so I'm trying to make a geometric picture of that. Furthermore, if this angle is alpha, we've projected out the cosine of alpha, the perpendicular, this is supposed to be in projection. This is a right angle right there. It looks like a parallelogram, but it's actually supposed to be a rectangle that I've drawn right here. It's just being looked at edge on. H bar over 2 cosine alpha is this vertical component. H bar over 2 times the sine of alpha would be this side or this side down here. So the length of this projection down here is h bar over 2 times the sine of alpha. And then if I label phi by this angle off the x-axis in the usual way that we do in three-dimensional spherical coordinate systems, normally we would call this theta, but I'm following Griffiths. He calls it alpha. If I call that phi right there, then to get the x component of this, I would take h bar over 2 times the sine of alpha times the cosine of phi. So this length, or this length over here, is going to be h bar over 2 times the sine of alpha times the cosine of phi to project onto the x direction. And that's exactly what this is. So it's like we've got a vector pointing in here, has length h bar over 2. We got the z component, we got the x component, and the y component is actually has a minus sign, but it would be sine of alpha times the sine of phi, which would give me this, but it's actually going back in this direction. So I think if I had drawn this correctly, the s corresponding to this would actually be exactly opposite to the way I've drawn it there, you know, put it through the z-axis direction. So that would give us the minus sign there. So this angle phi, its definition was gamma b0t. Phi is gamma b0t. And what that means is, as time goes on, that angle phi is going to increase, and that's going to cause this vector, as time goes on, to rotate around the z-axis, right? It precesses around the z-axis like this as time goes on. Now, this is just the expectation values of Sx, Sy, and Sc, but it's the closest thing we have to what is actually happening to the spin in terms of a classical picture that's going on here. Let's go back here and see what I've got shown here. Yes, so if we think of those three components together as the expectation value of the S vector, right? It has components Sx, Sy, and Sz. We're seeing that that expectation value of the S vector is keeping the same angle with respect to the z-axis, but precessing around it at a certain angular frequency, right? If we have a cosine omega t, whatever omega is, that tells us how fast it's spinning around the z-axis. And our omega apparently is gamma times b0. Okay, so this is called Larmor precession, after the first person to describe it. And omega, which is gamma times b0, is called the Larmor frequency. That means that the expectation value of the spin angular momentum changes as time goes on. That's not to say that we're describing the quantum mechanical state, but that's the closest thing to a classical description that we have in this case. You know, you can think of the electron, if it had, you know, if it were a classical electron and it had a spin, the magnetic field would be exerting a torque on it while it's spinning, and that torque would cause it to precess the same way a gyroscope precesses when it's feeling, you know, when we have a gyroscope, gravity is exerting a torque on it about its point where it's rotating. Maybe I have a picture in here. Somewhere, yes, I do here. So here's a picture of, you know, a top that's tilted at an angle alpha to the z-axis, right? Gravity is pulling down on it, right? So it's exerting a torque about the point where the tip of the top is hitting the floor. And that torque is in the direction tangent to the circle, if you like. And what that does is it causes the angular momentum to change in the direction of the torque. The angular momentum is, roughly speaking, along the direction about which this is spinning, and it causes the angular momentum to precess around in that direction. Here it's gravity causing the torque. In our case, it's the magnetic field causing that torque that we were talking about at the very beginning, because we got something that's sort of roughly like a current loop going on there. Okay. Again, I'm underlining something in the notes. We can't say the angular momentum itself precesses because the electron itself doesn't have a definite value of Sx, Sy, and Sz simultaneously. If you know Sx, you know you can't know Sy and Sz exactly because they don't commute. But the expectation values sort of give us the closest classical picture. All right, so we talked about earlier how, well, let me just ask this question. We can see what you make of it. Larmor precession means that when in a B field directed along the z-axis, the expectation value of the particle's spin precesses around the z-axis. True or false? It's possible to have this vector with these components point directly along the z-axis so that it doesn't precess with time. In other words, can I ever have this vector be aligned exactly with the z-axis so that as time goes on, the expectation value of the three components doesn't change? The expectation value of Sx would be 0, expectation value of Sy would be 0, and the expectation value of z would be constant, as it always is in this case. Let me just see your impression about that. Trying to give you guys enough time to think. Okay, well, so the answer is true. The reason I asked is because a lot of times people think, you can't do it. Remember before we said, it's never possible for the expectation value of Sz to, the measurement value to be definitely some value and its magnitude equal to the magnitude of the spin angular momentum. In other words, we said before, it can't align with the z-axis. That doesn't mean that these expectation values can't align with the z-axis. And in fact, we can see how to make alpha equals 0, right? Going back to our definitions, to make alpha equals 0, that would correspond to A equals 1 and B equals 0. That would give a case where alpha equals 0. And from our picture we just drew, that would have this expectation value thing lying along the z-axis. Or alpha equals, I guess, pi. That would mean alpha over 2 is pi over 2 would give a similar kind of situation. So it is possible that this vector we formed aligns with the z-axis, but we shouldn't think of that as telling us that we know simultaneously the definite values of Sx, Sy, and Sz. These are just the expectation values. I could get a value of Sy equals 0. Expectation value of Sy could be 0 by having two non-zero values of Sy that happen to have an average which is 0, even though there's two non-zero probabilities. Whatever. Maybe that was too much beside the point. Okay, so any questions about how to put in the time dependence? And this idea of Larmor precession is just sort of a take on how to make sense of the time dependence, at least in terms of the classical picture. Something as close as it can in quantum mechanics is precessing the same way a top would in classical physics, or something like that. I think Griffiths also mentions the connection to the Stern-Gerlach experiment that you talked about in modern physics. And so let's just remind ourselves a little bit about that. I remember after I took modern physics, all these names associated with experiments were just swimming around in my mind and I could never keep them straight. But this is the one where you get the beam of electrons, or the beam of actually atoms, silver atoms, splitting into two separate beams depending on the spin. And somehow that's supposed to tell us that the electron spin is 1/2 and that there are only two different possible values for Sz. Okay. The idea is, well, we talked about the net force on a spinning sphere, or on a spinning, as something that has a current loop, or more generally, a spinning sphere of charge. The net force, just like we found on our worksheet, will be 0 if the B field is uniform. And that's what we were assuming in that part of the problem. If the B field is non-uniform, in other words, if I take a bar magnet, right, and I look at the B field as you go away from the bar magnet, of course, the field lines get farther apart. We have a dipole field that would circle back around to the other side. So they're splitting apart. That means in this region, the B field's non-uniform. And if you think about what the force vectors are on all the little parts of this imaginary current loop here, they're not going to point directly outward from the center, but they're actually going to tip to one side because they have to be perpendicular to B. And B is sort of flaring outward everywhere on this current loop. And that means to be perpendicular to B, they have to point in one direction. And so there's going to be a net force on this current loop to one side. The same thing's going to be true of protons and electrons. If they have circulating currents and you put them in a non-uniform magnetic field, they are going to experience a net force. Okay, so let's think about our electron. Again, it's a little bit confusing because it's a negative particle. If it's spinning in the direction coming out from the bottom around the front and then in towards the top, so that means spin angular momentum is towards the left in that classical picture. Again, the gyromagnetic ratio is negative for an electron. That gives a magnetic moment pointing to the right in that direction. That's as if the current is flowing in the opposite direction of the spin kind of thing that I've drawn there. And in that case, that's going to generate a force to the left in this case, if we put it in this kind of magnetic field that I'm showing right there. So I imagine I'm sending a beam of electrons through, into the page of this diagram. So it's going through this region of magnetic field. If one happens to have its spin more or less aligned to the left, it's going to feel a force in the same direction that its spin is aligned. And similarly, if it's spinning in the opposite direction, the magnetic moment flips and the force direction flips. So if I send a beam of electrons through this magnetic field, some of them are going to, depending on which way their spin is oriented, and we know there's only two possible, if we call this the Z direction, along that direction. For some reason, drew it kind of sideways compared to the way we usually think of Z, only because that was just the best way to fit this diagram in here. So tilt your head sideways and think of to the right is up, maybe. Some of them are going to feel a force upward. Some of them are going to feel a force downward as I'm sending a beam through. But they should only feel two different forces because there's only two different possible values for spin, angular momentum, Z components. Okay, so this, if I take plus Z to the right, we would call this one a spin up electron. This one's a spin down electron. They're going to feel forces going in different directions. Classically, as you discussed in modern physics, we expect the spin axes of the electrons to be randomly oriented. And so there would be a whole continuum of different forces felt by those electrons. And we would expect to see kind of a fuzzy spot at this location, right? Some of them would feel no force if their spin was perpendicular to the field direction. And some of them would feel upward forces, some of them down, but it would be a smeared out spot. And as you discussed in modern physics, that's not what you see. You actually see two very discrete spots for those electrons. And that suggests that there are only two possible amounts that it could spin, at least along the Z direction. Okay, classically, we expect a smeared out distribution. Why isn't this working? Let's see. Oh, there we go. Okay. So that can be kind of useful, at least if you want a beam of electrons that's only spin up along the Z direction, you send them through a Stern-Gerlach experiment and you just throw away the ones that are on the bottom spot and you only keep the top spot, and that's your beam that's all spin up electrons. Well, I'm really having trouble with this thing. Not sure why this isn't working. Is my battery low? Or is the computer malfunctioning? For some reason, my clicker is not working very well. My pointer is working, but it's not advancing and going back on the slide. Now, just for the purposes of honesty, the original experiment wasn't done with bare electrons. It was done with silver atoms that have one unpaired electron in the orbitals associated with them. And that's because, practically speaking, bare electrons, if we send a beam of electrons through a magnetic field, they feel a huge magnetic force by virtue of the fact that we're sending an overall current through the magnetic field. And so, although there's no reason to expect that the result wouldn't happen with a beam of electrons, it's just practically undoable with electrons. So you do it with neutral atoms that have one unpaired spin electron. Boy, I guess this isn't working. Let me make sure. I may just have to click over here. It also shows us how we can measure the spin of a single electron. What you can do is just send it through the Stern-Gerlach apparatus, and the outcome of the experiment will be which side you see it appearing on, making a mark on the detector, the up spot or the down spot. Okay. Any questions on that stuff, which is yet another subsection of Section 4, Chapter 4, Section 4, Subsection 2. Now we're heading into Subsection 3, which is about addition of angular momenta. Any other questions on that stuff? That was more of a story than a calculation kind of thing. There aren't too many problems that you can do associated with that. Here we're doing in subsection 3, something where we'll actually be able to calculate things and ask nice problems. So this is something, if you're someone who strategizes about exams, here's some good exam questions in this section, not as much in the previous section. So we could say a single spin 1/2 electron, right? It has 2 degrees of freedom with respect to its spin. Again, we're not going to, in this section, pay attention to the spatial aspect of the electron. It has lots of degrees of freedom, infinite number of degrees of freedom, if we think about its spatial wave function. But if we just concentrate on its spin state, there are only 2 degrees of freedom, right? It could be spin up or spin down, or more generally, a linear combination of spin up and spin down. And that means that the space of states is a 2-dimensional vector space, right? And we're following Griffiths, we're going to say, once you've chosen your z direction, we'll denote those 2 states as spin up with an arrow up and spin down with an arrow down. Those mean spin up and spin down along the z direction. So, if we wanted to be a little bit more exact, we could say, well, that's spin up with respect to the z direction, spin down with respect to the z direction. That's one way to sort of give a basis for this space of spin states. It's a 2-dimensional space. We could also do the same thing with the x direction or the y direction or a direction that's in between x, y, and z. In either case, whatever axis direction you choose, there's always going to be only 2 linearly independent states, spin states along that direction. And any of those would be a perfectly good basis for the space of electron spin states. In this section, we're going to try to describe the spins of 2 particles. You could think of one application to be, we want to describe the entire hydrogen atom, ignoring the spatial wave function, which we already talked about, just thinking about the spin state of the hydrogen atom, where we got an electron and a proton. They're each spin 1/2 particles, and we're going to need a larger vector space to describe the spin state of a hydrogen atom. Maybe when I'm writing down these, the first vector describes, so we pick a z direction, and the first one describes whether the electron is spin up or spin down along that direction. And the second one describes whether the proton is spin up or spin down along that direction. And we have 4 possibilities. Both of them could be spin up, because they're both spin 1/2 particles, right? So there are only 2 possibilities. Or electron spin up, proton spin down, and so on. So there are 4 different possibilities. Sometimes in shorthand, if we know what the spins of the individual particles are, here the spins are both 1/2 and 1/2, we just specify what the M1 and M2 or M sub S1 and M sub S2 values are, but the arrows are supposed to indicate those two states. Now, it's a four-dimensional vector space if we've got two spin 1/2 particles. There are four basis vectors. But that's only one possibility for how we might make a basis for that four-dimensional vector space. Just like in three-dimensional vector space, you choose one set of x, y, and z hat axes. There are lots of other different sets of axes which would be perfectly good bases. They all have to have three basis vectors, right? If it's a three-dimensional vector space, there's got to be three basis vectors. Here we're talking about a four-dimensional vector space, so there's got to be four basis vectors. And we're going to talk about a different way of writing four basis vectors. Instead of describing the individual z component of the angular momentum of particle 1 and particle 2, maybe the electron and the proton, rather, we're going to try to describe the total angular momentum of the system and the total z angular momentum of the system by combining together the angular momenta of, say, the electron and the proton. Okay, or more generally, particle 1 and particle 2. So we're going to say, if I've got a total spin angular momentum operator, right? So I've got an Sx and an Sy and an Sz operator that operates only on particle 1, say the electron. And I've got an Sx, Sy, and Sz operator collection that only operates on particle 2. We could say the total angular momentum is just going to be the sum of the two angular momentum operators. And in particular, the total z component of angular momentum is the sum of the z component of angular momentum of the electron plus the z angular momentum of the proton. Okay, that sounds reasonable enough. We know how to form an operator Sz hat. We just take the one that corresponds to particle 1 and we take the one that corresponds to particle 2 for Sz and add those two operators together. And the idea is when we do this, this operator only cares about the spin state of particle 1. That's what the one means. And this one only cares about the spin state of particle 2. How are we going to calculate an operator that's associated or that is like the square of the total spin angular momentum? So that means combining together the electron and the proton. Well, one way to get S squared is to take S dotted with itself, right? If you take any vector dotted into itself, we get the magnitude of that vector squared. So we can calculate S squared as the S vector operator dotted into itself. And when we do that, well, of course, we can individually, kind of FOIL this out, if you like. So the first term dotted into the first term gives S1 dotted into S1, and that's by definition what we mean as the total spin angular momentum operator just concerned with particle 1 squared. The last terms, right, last times last, gives the square of the spin angular momentum of particle 2. And then we have two cross terms, right? I have an S1.S2 and I have an S2.S1, and I'm combining them together in the third term. There's an implicit assumption that those two operators commute with each other, right? Because I had an S1.S2 and an S2.S1 and I combined them together. They do commute with each other because one operator only cares about particle 1, the other one only cares about particle 2, and so they don't kind of interact with each other at all, right? If you do something that put an operator in front that only messes with the particle 1 state, that has nothing to do with what the particle 2 operator is going to do. So they do commute. So I can combine together those two terms by switching the order and just get, kind of the usual cross term that you would have done way back when you take the square of something. Okay, so that's summarized up here at the top. Now, here's the question that we want to answer in this subsection. What are the eigenvalues and eigenvectors of these two operators that we've just defined? We know what the eigenvalues and eigenvectors of S1 squared and S2 squared and S1z and S2z are already. That's kind of the description we've been using. But if we combine them together, we want to know what the eigenvalues and eigenvectors of the combined square total angular momentum and combined z angular momentum is. And how do we form those out of the old basis vectors, the up, down, down, and down, up kind of basis? We expect there to be 4 different eigenvectors of combined eigenvectors of these, or simultaneous eigenvectors of these operators, because it's still a 4-dimensional vector space, but we've got to construct it. So we already know that these good old states that we were talking about before, which just sort of describe both the z angular momentum of particle 1 and particle 2 separately, they are eigenvectors of the total spin z angular momentum and the total spin angular momentum of particle 1 squared and particle 2 squared. The claim is that their eigenvalues of all, their eigenvectors, these 4 things, are eigenvectors of all of these 3 operators. And what we're going to attempt to do now, because I know I've been talking about stuff, but maybe in a way that's easy for it to fly in one ear and out the other, let's try to think about, for these 4 states, particle 1 spin up, particle 2 spin up, and so on, up, down, up, down, down. Let's find, the claim is that all of those states where we're describing the individual z angular momentum of particle 1 and particle 2 separately, that they are eigenvectors of the 3 operators shown on the left of the table in problem 1. And we want to find the eigenvalues corresponding to those operators. So let's just do the upper left corner together, and then maybe I'll leave you to puzzle over the table a little bit. So we want to say in the upper left corner, when SZ operator, let me unshare the screen. When SZ operator operates on the state up, up, more generally, we're going to think of this as a spin 1/2 particle that we're just calling particle 1. Here's another spin 1/2 particle that's particle 2. And each one of them can be in a spin up or spin down state if we're describing their spin angular momentum separately. SZ, by definition, was just the sum of the SZ operator that only cares about particle 1 plus the SZ operator that only cares about particle 2. Okay, so the idea is let me just distribute that over it. So this is SZ1 operating on up, up, plus SZ2 operating on up, up. And now let's just think about what those are. What is SZ1? And again, when we're writing this, the implication is that the first one is particle 1, the second one is particle 2. What's SZ when it operates on this state, if this is SZ corresponding to particle 1? Well, what it does is say, I don't care about particle 2. Particle 1 is in the spin up state. So what is the SZ eigenvalue for something in the spin up state? H bar over 2. So this is H bar over 2. Again, it didn't really care what this one was in, times that, plus this one, same thing. SZ2 only looks at the second one, which again, spin up. So that gives a plus H bar over 2 times the same state back again. When I combine those together, I get H bar times spin up, spin up. And that means that the eigenvalue corresponding to the total z angular momentum, SZ, for this eigenvector is H bar. So we've shown that this is an eigenvector. We operated on it with that operator, and we got proportional to the same thing back, and the constant of proportionality is the eigenvalue. So the thing that belongs in the upper left corner there in that particular row and column is an H bar. Eigenvalue is H bar. So now think about, you know, you maybe don't have to write them all out, but think about what would have changed if I put an up down here and an up down here. That's the second one. If I put an up down here and an up down here, right? That changed to an up down. Well, the only thing that would change is we're going to get a minus sign for this one, right? And so the eigenvalue there is going to be 0. Remember, eigenvalues of 0 are perfectly fine. It's zero eigenvectors that are not allowed, but a 0 eigenvalue is no problem as long as the eigenvector is not the 0 vector. Okay, let's, I know you've started, I'm sure you haven't finished, but you're probably done most of the thinking that we want to do. So we showed that the eigenvalue for this state, for this combined total Z angular momentum operator was H bar. Everybody okay with this one being 0 because you get a minus sign between the two terms, right? This one operating on that gives an H bar over 2, and this one, sorry, when you switch this to down, this one operating on that gives a minus H bar over 2 times the same thing back again, so it adds to 0. Similar kind of thing happens here, and in this case, we get a minus H bar. Any question about those eigenvalues that go along with these eigenvectors? You know, we could have written it like this, but I'm just trying to use as little drawing as possible. What about S1 squared? Well, you know, S1 squared, again, when it operates on something like this, S1 squared operator, when it operates on this, it doesn't care about S2. It only looks at the first arrow. And we say, if you had a spin 1/2 particle, and S squared operated on it, how would you calculate what results? Well, again, S squared doesn't change the state. And what's the eigenvalue associated with S squared for a spin 1/2 particle? Well, it's S times S plus 1 times H bar squared. So it's a spin 1/2 particle. So S is 1/2. 1/2 times 1/2 plus 1 times H bar squared. That's 3/2, 3/4 H bar squared. We've seen that before. That's 3/4 H bar squared that it's going to pull out, and it doesn't change the state again. So this is indeed an eigenvector for this operator with an eigenvalue 3/4 H bar squared. How does that change for the up-down state? No change. It only looks at this one, and in fact, it doesn't care whether it's spin up or spin down. All that it cares is its total spin angular momentum, which is immutable for that electron or whatever the particle is. So this is 3/4 H bar squared, 3/4 H bar squared, 3/4 H bar squared. The same thing for the square of the total particle 2 square of the total angular momentum operator. It's a mouthful. 3/4 h bar squared. 3/4 h bar squared. 3/4 h bar squared. 3/4 h bar squared. The point is, going back to, you can look at your own table, but let's go back to the slide. We're interested in SZ and S squared, these operators. Now, SZ, we just said, hey, our good old friends, up, down, up, down, and up, are all eigenvectors of this new operator we formed. S squared has these two pieces in it, and at least with respect to these two, our same good old friends, up, down, up, down, are eigenvectors, and we just found the eigenvalues in the table. The hard part is going to be this last term, those cross terms, and we're going to have to work on that a little bit more. The claim is that these four old states where we specify their indefinite states of particle 1 and particle 2, z spin angular momentum, those are eigenvalues of the ones we just looked at, but they're not eigenvectors of S squared because they're not eigenvectors of that cross term. Okay, so this is going to be a problem for us, or it's going to make us not use this basis anymore. Here's how we're going to chip away at that. So let's start looking at this term. It's 2 times the dot product between these two operators. And a dot product can be simplified out in terms of the products of the components, right? So we can write S1 dot S2 as Sx of particle 1 times Sx of particle 2, and sum of that for the y's and the z's. So, there's a lot of work to be done here, but what I want you to do is think about what happens when I apply sy1, sy2, that operator that's in the middle right here, on the state up, and that's worksheet problem 2, just to kind of get the idea, and then I'll summarize what happens in the other cases. Again, anything with a 1 on it only cares about the particle 1. Anything with a 2 on it only cares about particle 2. To do that, of course, it's not the same as SZ, right? Because this is an eigenstate of SZ, but we can use our old, what I've given you here is the SY operator. The SY operator we worked hard to find out before was h bar over 2 times 0 minus I, 0. And so we're going to apply that to the particle 1 state and the particle 2 state, and so on. See if we can simplify that. Okay, so what we've got to do is sort of separate this out into the particle 1 and particle 2 stuff and write it in terms of spinor, 2-element spinor notation, right? Because that's what we know the 2x2 matrix for SY for. So when I write this arrow, up like that, we said in terms of our 2-element spinors, that means 1, 0, right? That's our spin up state. And this one is in a state 1, 0. So this is the state of particle 1, this is the state of particle 2. And then this is something that operates on that. So I'm going to take all the particle 1 stuff and put it together and see what results from it. And then I'm going to take all the particle 2 stuff, let it operate on there and see what results of it. And then we'll interpret it, what happened after all that. So in this case, when this matrix operates on 1, 0, I get, let's see, I get 0 for the upper element and the lower element gives an I. So it looks like this simplifies to h bar over 2 times I 0, 1. Tell me if I make a mistake there. I think that's right. And particle 2, this is the same exact calculation. So I get an h bar over 2 I 0, 1. And so if we were to write that in terms of this notation, we would say, well, each of these got some factors out in front of it. So we get an h bar squared over 4. I times I is minus 1. And then we're left with this state of particle 1 is spin down and particle 2 is spin down. So we could write that in our really shorthand notation like this. So SY1 times SY2 as an operator, we've shown that this is not an eigenvector because it's not proportional to itself when it operates on it. It totally changes the vector into some other vector, right? And generically, that's what happens. So let me just, any questions on that calculation there? I'm just trying to do the details. It's too easy to like nod your head when you're reading through Griffiths and not really get the details of what's going on. So we're just sort of sampling some of the calculations here. Okay, so what we get is, this is the result for SX1, SX2 operating on up, up. It's plus h bar squared over 4 down, down. Here's the one we just verified. It was minus h bar over 4 down, down. That's from SY1, SY2 operating on up, up, and it gives minus h bar squared over 4 down, down. And here's the SZ operating on that. It gives plus h bar squared over 4 up, up, because that is an eigenvector of SZ1 and SZ2. These two terms right here cancel each other, right? They add to 0, and therefore I'm just left with the third one, which is h bar squared over 4 up, up. So it turns out, though it wasn't clear things were going to go this way, that in terms of that cross term, which had a 2 out in front of it, but the important part is here, that cross term in the operator s squared, this state up, up is an eigenvector of that cross term, and the eigenvalue of just the cross term is h bar squared over 4. That's not going to be true for all the other possibilities. In other words, up, down, you would find out you didn't get that fortuitous cancellation, and it's not a simple combination anymore. So here's the, if you do that, not just for the up, up state, but for the other 3 possibilities, here is, oh, let's see, problem 3. Maybe I force you to do it. Yes, okay, so we've got the yes, okay, so in this case, we're just looking again at the up, up state here, and we want to put everything together. S1 dot S2 operating on up, up is, we found, is equal to h bar squared over 4 up, up. That's summarizing what we just did in the previous problem, or what we found following the previous problem. Now we want to find s squared. Do I have it written anywhere on here? No, but remember that s squared as an operator, the total combined spin angular momentum squared operator, was expanded out as S1 squared plus S2 squared, S2 squared plus 2S1 dot, I guess we should write it this way, S1 dot S2 vector. So when this operates on the up state, this operates on the up state, and the result of it is in your table. This operates on the up state, the result of it's in your table. And this one we just worked out. So combine those all together and tell me when S squared as an operator operates on the up state, what results? Okay, let's try to pull together the pieces because we've got all three of these already worked out, right? We're saying, what happens when this is applied to the state up? Well, that's the same as this being applied to up. Forgive me that I don't put the vector notation in there because I'm trying to squeeze it in. And the result of this is in your table in the second row, first column, right? When S1 squared operates on up, you get 3/4 h bar squared times up back again. Same thing's true for S2 squared. So the result of this is 3/4 h bar squared up. And we just said, we only did part of the calculation, but this is summarized at the top of problem 3, that when S1 dot S2 operates on up, you get h bar squared over 4 up, and we've got an extra factor of 2 out in front. H bar squared over 4 up. And so the result is all proportional to up. What do we have? 3/4 h bar squared plus 3/4, that's 6/4 h bar squared plus 2/4 h bar squared, that's 8/4 h bar squared, which is 2 h bar squared times the state up. And at this point, Griffith says, well, you know, let's just write this in a suggestive way. We're going to write this as 1 times 1 plus 1 h bar squared, which will make sense. You know, it looks like an s times s plus 1 h bar squared. In other words, it sort of, at least, you know, very superficially matches the pattern of an s equals 1 state, right? Little s equals 1, or total little s equals 1. Okay, so that's just, you know, part of the calculation. Now we got to do it with up, down, and down, up, and down, down. Oh my God, it's a lot of work, but you see in principle kind of that each step is pretty easy. Okay, so there's the result. We're going to write it this way for the up state. here's the result for the down state. You also get 1 times 1 plus 1, or 2 h bar squared times the down state back again. The interesting cases are the ones that are not up, or down. When s squared is applied to up, down, you don't get just up, down, back again, but you get a linear combination of up, down, and down, up. Okay, let's hold on to that. When s squared is applied to down, up, you get, again, some linear combination of up, down, and down, up. You know, it's sort of a complicated combination of those two states. We could simplify that a little bit, but we don't really need to, because remember the point of what we're looking for. We're looking for states that are eigenvectors of the total spin angular momentum squared. This is not an eigenvector. Up, down is not an eigenvector. I should point with the clicker so that Alvis can see. This is not an eigenvector of s squared. I can see, look, because I don't just get up, down, back again with some constant out in front of it. This is not an eigenvector of s squared. These two are. But we can now just sort of by luck see how to form an eigenvector out of these things that is an eigenvector of s squared. Notice that if we add these two states together, so we take the state up, down plus down, up. Okay, let me just write that on the board so it's not. If we take the state which is a linear combination of these, up, down plus down, up, and we let that total spin angular momentum squared operator operate on it, well, we can see what the result is by combining those two results that we had shown right here. I know what happens when s squared operates on up, down. I know what happens when it operates on down, up. Now, here's the result. Since what we're concerned with is the sum of the left-hand sides, I can just sum the right-hand sides together. And when I sum the right-hand sides, you have to kind of look at, you know, it's a little bit jumbled here. Here's an up-down state. Here's an up-down state over there. I get a 2 times that minus 1 times that gives me 1 times that. You'll find out that even though these individually aren't eigenstates, that when we add or subtract up, down, and down, up, we will get eigenstates of s squared. So Griffiths suggests, because both of these, you know, by virtue of the fact that 2 can be written as 1 times 1 plus 1 times h bar squared, they're sort of looking like s equals 1, and we're going to make up some new labels associated with these states. We're going to say there's a total spin angular momentum combined quantum number for the squared total spin angular momentum. We're going to call that just s, not s1 or s2. And when we have s equals 1, we could have the z component be either 1, minus 1, or 0, right? It goes from minus s to s in integer steps. We'll find out that when s squared is applied to this state, which is defined to be the normalized sum of those two old states, that we get 1 times 1 plus 1 h bar squared back again times the same state. Okay, that's not immediately obvious. You'd have to follow the details through. So this particular sum, when I normalize it, it's a normalized eigenvector of the s squared operator. And of course, since each of these are individually eigenvectors of the sz operator, it's a simultaneous eigenvector of the total spin squared operator and the total spin z operator. And it seems to correspond to a quantum number of s equals 1 again, just like the other ones did, because the eigenvalue is 1 times 1 plus 1 h bar squared, or 2 h bar squared. Whereas when we take the difference between those two states and normalize it to make a normalized eigenvector, and we apply s squared to it, we'll find we just get 0 as the eigenvector. And we're going to write that suggestively as 0 times 0 plus 1 times h bar squared, still just 0, but the eigenvector is 0. So that's sort of like a total spin quantum number of 0. And so we can sort of think of there as being two kinds of states of eigenvalues of total spin squared angular momentum and spin z total angular momentum. There's a triplet of states corresponding to a quantum number s total equals 1, which has sz quantum numbers going from -1 to 1. That's what's shown in those left kets there. And we've just found out, or at least I showed some of the evidence along the way, that it's certain linear combinations of the old ways we described it, right? So what this means is, when I write these arrows, this is a description of what state particle 1 is in and what state particle 2 is in. When I write it this way, I'm not giving separate information about particle 1 and particle 2. Rather, I'm giving an information about the combined total squared spin angular momentum and combined total spin z angular momentum. So this is just combining everything together, whereas this description is just describing individual particles. So we call that the s equals 1 triplet state. And then there's another state down here, which looks like it corresponds to quantum number s equals 0, for which there's only one m sub s value, and we call that the s equals 0 singlet state, because there's only one m sub s value if s equals 0. So these are the combined quantum numbers, combined total spin angular momentum quantum number and combined spin z quantum number. So this collection of 4 states, we knew we were talking about a 4-dimensional vector space because we have 4 basis vectors, up, 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 down, down, up, down, down. Here's a different, sometimes more useful set of basis vectors. Because, you know, if a particle decays, and that particle that decays maybe is in a state s equals 1, m sub s equals 1, or something like that. If spin angular momentum is conserved, it's not, because the angular momentum might get mixed with it, then after the decay, we know that the individual part, we don't know what their individual states are, but we know what the combined state is if angular momentum is conserved. So in some sense, this is a more convenient basis, and we'll do some problems soon enough, probably not today. Okay, so this is just to summarize. Here's the old basis. Now we've got a new basis. Of course, there's got to be 4 basis vectors. And it takes you really have to think about this 6 or 7 times before you really understand what's going on. The notation kind of gets in the way there. These are describing the total spin state. These are describing the individual spin states. Neither one is better than the other one, but sometimes one's easier to use in a particular situation. Now, this is just one example of a kind of bigger, more general problem, which has to do with what's called Clebsch-Gordan coefficients. We were doing the example of spin 1 equals 1/2, spin 2 equals 1/2, combining angular momentum. What happens if we have a spin 1 particle and a spin 3/2 particle? How do I find the eigenvectors of the combined total squared spin angular momentum and total spin z angular momentum in terms of the individual z spin descriptions? Okay. And it was already a pain to work out this case. If try S1 equals 2 and S2 equals 3/2, you'll be there all day trying to creatively make eigenvectors and figuring out what all those eigenvalues are. But of course, somebody spent all the time and done all the work for you. The argument above, sort of, we got lucky with it. We used the sums and differences, and we just sort of said, oh, look, if you take the sum and difference, it looks like it works, and those will be the eigenvectors. If you're not feeling that creative, and in general, you can't be that creative, you can always find the eigenvectors of this new operator, sort of an old-fashioned way, but just by using matrices that correspond to the different operators that we're concerned with. So let me just end by showing you how to do that. This isn't something that we're going to calculate with, but here what I'm going to do is define my basis elements as in the descriptions of the individual particles, right? So if we say we're talking about 2 spin 1/2 particles, and so there are 4 possible spin z states if we take both into account, the up, 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 down, up, and down, down states. And I'm going to write the total spin angular momentum squared operator as a 4x4 matrix in that basis. So I'm going to fill out what the elements are, right? Well, I know we already figured out in our table that, or from our work before, that when S squared operates on the up, up state, it gives 2h bar squared times the up, up state back again. And by using information like that and figuring out what all the 8 matrix elements are, I could fill in all 16 matrix elements of this operator, okay? I'm not suggesting you do it, but it's just to reassure you. And then I could say, hey, there's an operator. Let's find its eigenvalues and eigenvectors. So I could let that, I would say, here's an eigenvalue, arbitrary eigenvector, and we're going to require that it's lambda times the same thing back again. You write the characteristic equation down and look for what the eigenvalues are. You'll find that there are only 2 eigenvalues. S squared is 0h bar squared, or S squared equals 2h bar squared. And then we would do the usual process. It's kind of a pain to find the corresponding eigenvectors. And that would tell me how to write, states of total squared definite angular momentum in terms of the individual states' angular momentum descriptions, right? So if you're, well, here's the combination we found before, that for a total spin angular momentum eigenvalue of 2h bar squared, there was one that corresponded to sz equals 0, and it was this particular linear combination of up, down, and down, up. Okay, I'm not going to say any more about it because I'm not suggesting you do this, but it's just saying you don't always have to be as creative as eyeballing and saying, oh, just take the sum or the difference. When things get more complicated, you're not going to be able to just eyeball it. You have to have a more systematic way of doing it, and Griffiths doesn't really tell you anything about that. Okay, maybe we'll stop there because I feel like that's way too much for today, and we'll finish up finally chapter 4 tomorrow and then get into chapter 5.1 on Monday. I feel like we'll have enough material for most of the end of chapter 4 tomorrow because we've still got more practice problems to do. If we end a little bit early, that's just the way it'll be, just to not start into something new on Friday. All right, it might help because you read this a while ago to go back and look at Griffiths and try to follow the line of argument. His is a much more high-level argument where he's not showing any of the details. I was trying to give you some of the details along the way, but there's arguments in favor of both where sometimes you give too many details, you get lost in the weeds. I was trying to give just enough, but maybe in a 2-hour class meeting, that ends up being too much for one day. All right, and it's my intention, I've fallen behind on updating the website, but I'm going to put up one more chapter 4 homework, and it's going to have to do with the stuff that we're talking about right now, Clebsch-Gordon coefficients, which we'll talk about tomorrow. It'll be due mid next week. I'll probably make it due Wednesday, and then I'll push it back so that you can turn it in on the exam, but you should try to have it due Wednesday so that you have a chance to ask questions on it before Thursday's exam. All right. See you guys tomorrow.
Have a good day.
All right, see ya.
Go.